that says if there's a debugger attached or not. You can set this value from userland. It's checked via the system call or the library calls, is debugger present, and check remote debugger present. There's also NT query information process for the debug port information. Debug port is 0 if there's no debugger attached, or it's non-zero if there's a debugger attached. That's a system call. And then you can write code to the break-in function for when a breakpoint happens, or when a debugger is attached. The attaching process calls these two functions in NTDLL, and if you write your own code there, you can get it to execute and notify you that there's a debugger there. KakiWare has this little utility called anti-debug that uses this technique. You can also check your parent process ID to make sure that you weren't launched in a debugger, and you can call this system call to try and hide your thread from the debugger. This doesn't. This only prevents. This last one doesn't make your thread invisible. It just prevents you from receiving exceptions for that debugger. Going on, there's that exception checking that I mentioned earlier. You write the breakpoint instruction, and then you verify that your handler gets the exception. The same idea can be used to try and detect the closed memory in Tron. You can also check wall clock times and make sure that there's no large amounts of time passing between breakpoints. And then you can check your window titles of other windows on the system to make sure that there's no WinDebug window open or IDA window open or OllyDebug window open. And then you can check the list of running processes as well for those same things. So what does ADHD cover out of this? It covers most of them, most of the ones that were easy to do and weren't done elsewhere. It resets that userland flag just for you. You could do it yourself, but it does it automatically. And it also hooks that NT query information process and zeroes out the debug port, so it always returns zeros if there were no debugger present. And it actively monitors debug UI remote break-in and debug breakpoint for hooks. Every time there's a create thread, it verifies these functions and makes sure they haven't been modified from the originals. And we've tested it successfully defeats KakiWare's anti-debug. It also resets your parent process ID to Explorer automatically if it's not Explorer, so that's handy. And then lastly, it just completely blocks thread hide from debugger to prevent it from actually hiding the thread. So what is it missing? Well, exception redelivery, basically that writing a breakpoint issue. You can also do the same idea with dereferencing a null pointer and making sure your exception handler triggers right away. But IDA and WinDebug both have options to pass these things through, so you can get around that without ADHD. It also has, there's a big problem with spoofing get the time functions. They're not really hookable from the kernel. They're used via shared memory. So your best bet for getting around these is trying to script your timed areas of execution using a scripting language for your debugger or macros. And it also doesn't do process or title cloaking. Clue, the IDA plugin, does spoof IDA's Windows title, and you can try and use Futo, the process cloaking rootkit, to try and hide your debugger process from being noticed. So, finally, we have librootkit. Now, I probably should have left that graphic up there for a little while longer. There's Pac-Man in the corner of that graphic. I find that amusing. We got annoyed-looking Stark over there. Okay, so what are the noteworthy librootkit APIs? Well, you have hook.syscall that you can hook a system call by name. This is basically used for an OS-independent method of hooking system calls without having to worry about what the slot is in the system service table from OS to OS. is actually based on a rootkit.com post by Gareth. Was improved. The interface was improved a bit, and it actually frees the resources and the section mapping and so on. And the setup hot patch is really sweet. It basically sets up a detour style trampoline using Nicholas Capin's x86 length decoder to make arbitrary instruction modifications and function modifications to things like the scheduler, which Tron uses. There's also a pro for read and pro for write status, some other helpful things that utility functions that are in there. Borrowing memory, userland memory from the TED. A function to get the shadow table and set the interrupt vectors, and some logging functions. So hopefully that's useful to somebody. Next is Clue. So this graphic's another fun one. I like that. Wanted to put a little thing off his mouth that I fear data rescue. They both threatened to expose me, and their API is broken, so I don't really have too much love for these guys. But actually, they may be here. So Clue. Clue will hook IDA's debugger functions to actually set hidden breakpoints with Tron, so that you can set hidden software breakpoints using IDA, and make these breakpoints unable to be detected by your debug process. The problem with the random system problems, the IDA 4.9 and IDA 5 debugger API is kind of insane. They have these functions that you basically install hooks for: write memory, read memory, add breakpoint, and del breakpoint. It never uses write memory to write the breakpoints, and it also randomly writes to these breakpoint memory in between the adding and deleting breakpoint calls. So it's sort of just like haphazardly writes to your memory. I don't know how you're supposed to develop like a remote debugger with this. So we had to use the Microsoft Detours library, which is sort of like the userland equivalent of our setup hot patch, to detour write process memory from IDA to hook it to see if it was writing a breakpoint to our pages, and then write the breakpoint via Tron instead. And then Clue also changes IDA's window titles to random strings to avoid detection. So that covers the window title enumeration issue. So here we have talk setup. Basically, first we made the orange anonymous, and then we went on to making a human anonymous. It doesn't really hurt quite so much, so that's okay. So components, what went into this? Well, we have the speaker laptop. This has a Ventrilo client. Talk setup. Oh, I'm gonna pause for the audio. Has the audio caught up? I show components here, so I'm gonna continue. So we have the speaker laptop has a Ventrilo on it, voice changer, VNC client to connect to the desktop to handle a mouse, and of course Tor. The speaker side on my side has a firewall to prevent the voice changer and Ventrilo from phoning home. It seems that you could turn that off if you disable update notifications for both of them. They didn't seem to try and phone home this time, but I don't know if I fully trust them either. So the Linux, we created a Linux VMware image to basically ease setup on the audience side. So we created a Linux VM image to each setup on the audience side. We use GNOME's remote desktop VNC server to give us access to the desktop remotely. Put the talk slides on there, PDF reader, and then install the Linux version of Ventrilo server and the Ventrilo client running in Wine. The various hacks we had to do to get the Ventrilo running in Wine are documented in the published paper as part of the proceedings. Last two components, of course, plenty of paranoia, possibly somewhat needlessly, but just for fun. And then also just for fun, fuck the man. Local setup. So Ventrilo has UDP traffic that you need to block. So it tries to connect to the server via UDP. That's probably not so much an issue when you're tunneling it through SSH, but just in case the IP is negotiated somehow, as is done with VoIP software often, we blocked all the traffic except for the stuff destined for our Tor router and the Tor directory servers at the firewall machine. We also set up, created a custom Tor RC to allow us to attach our own our streams to our own circuits, and then we had to tunnel VNC and Ventrilo over SSH. And then we had a nice little echo script running, so we could tell if we dropped. This echo script has been fairly continuous. So I guess there's just random buffering causing problems with backlog for voice. Hopefully it's not been too annoying. And we haven't dropped, so that's a plus. Okay, so here's a diagram of what all this looks like. So you've got the firewall over here going over 802.11. This is optional 802, public 802.11 is available or whatever. It's not so much of a concern hiding this endpoint unless you're really worried about a global adversary or a large number of Tor nodes being surveilled. As you can see, there's only really one Tor circuit needed. We were able to multiplex VNC and Ventrilo over the same SSH connection, forwarding those ports over Tor through the internets, and then onto the display computer, the display computer's VMware image. The fake flows down here, that's an option if you want to try and create a larger confusion set, if you're worried about some data retention or a global adversary, if you're speaking about highly sensitive material where someone may actually use Echelon to try and watch you or what have you. The other option is you could try and run a Tor server from your speaker location. This will keep connections alive to nodes for a long amount of time. As I discussed in the paper, really the vulnerability point from here is you have a circuit that's going to be very long, have not that much data flowing through it, and have a sort of a signature pattern, bursts of this voice traffic going through, and then a little bit of data for slide changes and mouse events. And it also happens to be going on for the exact time duration that the talk is going on. So if someone does, you no longer need to capture both Tor nodes in order to notice with a fair degree of certainty that you have the right circuit. You only really need the first one, and you only really need to surveil the first one externally. So what you can do against an adversary that's able to surveil the first Tor node externally is you can run a Tor server that's going to make long-lived TCP connections to numerous Tor nodes and keep them alive so long as circuits are flowing through those connections. And then you don't really have to worry about making a single TCP connection to a Tor node that only lasts while you're giving the talk, because your circuit will reuse an existing connection to whatever Tor node you choose. And then the Linux VM that we use to do this is redistributable. If anyone wants to seed, Henry K. and I guess the 23C3 admin should have a copy of this. maybe toss that up on the website or whatever. I don't know. Maybe it's necessary, maybe it's not. But main problem